In this video now we'll talk about reacting solutions of weak bases with added strong acids. And we'll look at the unique situations for problems we create there. Let's consider 1 liter of a 0.050 molar hydrazine solution. Now hydrazine is one of our nitrogen-containing compounds, right? As a nitrogen-containing compound that's going to act as a weak base. It doesn't have its own hydroxide ions, and so it tends to react then with water to create hydroxide ions, right? So we have our N2H4, right, in our water, and it will create an equilibrium where you get N2H5 plus a hydrazonium ion plus hydroxide ion, all aqueous, right? So that creates our equilibrium, right? And the Kb for that process is known, right? The Kb is 1.3 times 10 to the minus 6, right? We don't have any dissociations. There are no complete processes for us to consider, so we can go straight into our ice table. Initial change, equilibrium, right? We got 0.05 of that. We got that's liquid, so right, we don't have to worry about that. Its activity is 1. We've got none of that. We got none of that, and so x of that will have to dissociate. It will make x of that. It will make x of that. Right? We have 0.05 minus x, x and x. If we put that in our equilibrium constant expression, and oh, by the way, let's remember, since we have a small equilibrium constant, right, we can make the assumption that that x is small enough that we don't have to consider it in that subtraction, and so you end up with 1.3 times 10 to the minus 6 is equal to x times x divided by 0.05, right? So when we multiply through by the 0.05, we get 6.5 times 10 to the minus 8 is equal to x squared. When we take the square root of that, we get about 2.55 times 10 to the minus 4 is equal to x. And in this case, right, we always have to look back and remember what we defined x as. Here, x is the equilibrium concentration of these two, but it is the hydroxide ion concentration, right? And since it's the hydroxide ion concentration, we have to remember that the concentration of hydrogen ions, right, if we use the Kw, is 1.0 times 10 to the minus 14 divided by our 2.55 times 10 to the minus 4. And so we get the concentration of hydrogen ions is 3.92 times 10 to the minus 11, which then when we take the log of that and the negative, you get that the pH is 10.41, right, to two significant figures, okay? So there's our straightforward dissociation of our weak base in water, right, reminding us of that reaction. So let's talk about this system now, right? We start with 1 liter of 0.050 molar hydrazine, and we're going to add 0.020 moles of nitric acid to that, right? And since nitric acid is a strong acid, that means we have to consider a complete process, right? So what would be our complete process? Well, it's going to be hydrazine plus nitric acid to make right? The hydrozonium ion plus the nitrate ion, right? Again, all of those things are aqueous, right? And so if we consider, right, it is a complete process, so we have to work it in moles, but since I was nice and put this in 1 liter, it's easy to figure out how many moles we have, right? So for a limiting reactant problem, you have to work in moles. And so we've got our initial, we've got our change. Because it's a complete process, we have a final state, not equilibrium. And so we have 0.050 moles of hydrazine. We have 0.020 moles of nitric acid. No hydrozonium ion, no nitrate ion, right? Since it is a limiting reactant problem, right? All of our limiting reactant will react, leaving none of that, but that will determine how much of the other things change. And so we end up then at the end with 0.030 moles there, with 0.020 moles there, and with 0.020 moles there. And so that is how we handle our complete process first, and then we can move to the equilibrium process, right? So if this was 1, right, 2 is doing our equilibrium process, right? Where we use the results of our complete process. Now, just right as a preview, because we're going to run out of space here, right? Remember our equilibrium reaction that we used before. Let me give myself a little more room. Right, was in 2H4 plus hydroxide ion. Oh no, that's not right. Getting ahead of myself. Plus water creates an equilibrium to create hydroxide ion plus hydrozonium ion. And the difference is here, if we're considering, right, our initial state, right? In our initial state, we've got some hydrozonium ion, and we've got some hydrazine, right? And so that will become the starting point for considering the equilibrium part of the reaction. Right? So here's where we ended up on the previous slide, right? We've got our hydrazine reacting with water. The water's liquid to make hydroxide ions plus hydrozonium ions. And we had our initial concentrations that were determined after the complete process, where we had 0.030 molar hydrazine left after the complete reaction, and we had made 0.020 molar hydrozonium ion, right? And so, right, water is a liquid, so its activity is going to be 1, right? We don't worry about that. But we haven't considered that we've made any hydroxide ions yet, right? So our change, right, we got to make some hydroxide ions to establish an equilibrium. That's going to make some hydrozonium ions at the same time, and it's going to take away from our hydrazine. This is an equilibrium, so we can consider an equilibrium position. Right? We add those up, and again, right, our Kb was a small number, 1.3 times 10 to the minus 6, right? And so since we have a small equilibrium constant and concentrations much higher than that, we can make our assumption that we can ignore the x. And so then you end up with, right, 1.3 times 10 to the minus 6 is going to be equal to x times 0.020 divided by 0.030, right? If we multiply that through, you get 1.3 times 10 to the minus 6 times 0.030 divided by 0.020 is equal to x. That then is equal to 1.95 times 10 to the minus 6. But we have to look, right? That ends up being the equilibrium concentration of hydroxide ions. Right? So to find the concentration of hydrogen ions, right? The concentration of hydrogen ions is going to be our Kw divided by our 1.95 times 10 to the minus 6. And we're going to get out of that 5.13 times 10 to the minus 9 molar, and that makes our pH 8.29. Okay? So there's how we would do a reaction of a weak base, in this case a nitrogen-containing base, right, with a strong acid, right? We did that complete reaction on the previous slide, and then we dealt with the results of that reaction in establishing our equilibrium. Okay, so our other major class of weak bases we deal with in general chemistry are salts, soluble ionic compounds of the conjugate base anions of weak acids, right? So here we have sodium butyrate, right? We've dealt with butyric acid in other videos. So just to remind ourselves, right, we still have to deal with complete processes first. And in this case, that complete process is the dissociation, right? The dissociation of the sodium butyrate. Maybe we're getting comfortable enough now to accept that if we have 0.20 molar sodium butyrate, that when that dissociates, we're going to end up with 0.20 molar butyrate ion. Right? If you're uncomfortable with that, go back and watch the previous video where I go through that in detail. So we have to consider the complete process first, and then we can consider the equilibrium process, right? We always go through that in order. Complete processes, then equilibrium processes. Okay? Now, the problem is, all we've got is this, which we said was a conjugate base, right? So we're left with a solution where our only chemically active ion is a base. And so our equilibrium is going to be that ion, our butyrate ion, right, reacting with water to form. There's a little bit of butyric acid. I got excited. Plus hydroxide ions, right? Now, that's great, except all we have up here is the Ka, right? So now, since this is a base dissociation, we need a Kb. This is where we can remember that Ka times Kb is the Kw. So the Kw, 1.0 times 10 to the minus 14, divided by the Ka, 1.5 times 10 to the minus 5, gives us our Kb, which is 6.667 times 10 to the minus 10. Okay, so now we know our Kb, we've got our equilibrium, and at least we know the initial concentration of our basic anion. So now we can start to work the equilibrium problem. Right, so here's where we ended up on the previous slide, right? We've got our butyrate ion as the only basic thing in there that can react with water to make butyric acid and hydroxide ions. That's what we're looking for. We found the value of the Kb, which I had to crowd in there around my controls, and we knew from our complete dissociation that this was the concentration of our butyrate ion. So now we've got initial, change, equilibrium, right? We've got, right, that's liquid, so its activity is 1. We got none of that initially, none of that initially, minus x, plus x, plus x, 0.20 minus x, x and x, right? We've been through this before. We've got a really small equilibrium constant, so we can ignore that. And so we end up then with an expression that looks something like this, that are 6.667 times 10 to the minus 10 is going to be equal to x times x, getting a little excited there, divided by 0.20, right? And so when we multiply that through, you get 1.333 times 10 to the minus 10 is equal to x squared. And then you get 1.155 approximately times 10 to the minus 5 is equal to x. But that is the concentration of hydroxide ions, right? So our concentration of hydrogen ions is going to be ERKW 1.0 times 10 to the minus 14 divided by 1.155 times 10 to the minus 5, and that is then 8.66 times 10 to the minus 10, which when you take the log of that, you find that the pH is 9.06. Okay? So, right, reminding us how to deal with a problem where we have a basic salt in solution by itself. Now let's react some of that salt with nitric acid. Here we have, right, our solution of our basic salt, right, our sodium butyrate, right, and we're going to add 0.04 moles of a strong acid, nitric acid. Now, right, here's our problem, right? We know that we do complete processes first. But here we have multiple potential complete processes, right? We've got potentially the dissociation of our sodium salt, right? That if that dissolves, that will dissociate completely. We could consider the dissociation of our strong acid, but we've also got the potential acid-base reaction between the two. So I find it most productive to go complete reactions first, then processes like dissociation. Right? So if you consider the complete reaction first, then any dissociations that are left over, the process becomes a little more straightforward. So let's look at what our reaction would be, right? Our nitric acid would be our acid. Our sodium butyrate would be our base, right? Now, there's no, right, this is going to have to be a Bronsted-Lowry acid-base reaction. We're not going to be able to produce water, right? But we're going to end up then with butyric acid, right, plus sodium nitrate as I run out of space at the edge, right? Poor planning, right? And so now we've got a complete reaction that we can deal with. We can look at our initial amounts, our change, and since it's complete, it would be final. And again, when we do these, we work in moles, but since I was nice and gave you 1 liter, it's an easy conversion. So we're going to have 0.04 moles of nitric acid. We're going to have 0.20 moles of sodium butyrate. We haven't made either of these yet, right? And so since it is a limiting reactant problem, our nitric acid, since they're 1-to-1, is the thing that will be limiting. We will react all of it, which will determine how much the change is for everything else. Right? And so you will end up with no nitric acid left, less sodium butyrate, some butyric acid, and some sodium nitrate. Okay? And so now we can consider complete processes, right? Now we can go to processes that might affect our equilibrium. And so we can focus then on this leftover sodium butyrate, right? So, right, if this was A, right, then B, we focus on the sodium butyrate. And, right, this is what we dealt with, right? If we have 0.16 moles of that, and it all dissociates, we're going to have 0.16 moles of our butyrate ion, right? And so, right, if we remember that and we're comfortable with that, now we have some butyric acid, some butyrate ion, and now we're ready to go to step 2 and consider our equilibrium process. Right? When we consider our equilibrium process, as we realized on the last slide, we actually have some butyric acid now, right? And it can form an equilibrium with hydrogen ions and butyrate ions, right? And if we look at our amounts, right, we had 0.04 moles in a liter, so that's 0.04 molar, and we had 0.16 moles back in that same liter to make it easy, right? And so we can, right, consider we don't have any hydrogen ions yet, minus X plus X plus X, 0.040 minus X, X, 0.16 plus X, right? We can do our, right, make our assumption. And if we remember the Ka for this was 1.5 times 10 to the minus 5. That's going to be equal to X times 0.16 divided by 0.04, right? So X is going to be equal to 1.5 times 10 to the minus 5 times 0.040 divided by 0.16, which is going to be equal to 3.75 times 10 to the minus 6 molar, which is the concentration of hydrogen ions moving up here where we have a little space, right? Therefore, the pH is 5.43 approximately. Okay? So in this case, even though we were titrating a base with an acid, in the end we could use, because we had created some of the conjugate acid-base pair, we could use the acid equilibrium to determine the final pH of our solution. So there are a couple of different ways to look at reacting solutions of weak bases with strong acids.